Hello, hello, can you hear me?
Yeah, can you hear me?
Yeah, yeah.
Yeah.
Okay. Hi, how are you?
I'm good. How are you?
I'm good, I'm good. I think we met a long time ago when you were a small kid.
Oh,
Do you remember?
no, not really.
Your brother was studying, and I used to come to Purva Fountain Square.
Yeah, I must have been. Yeah, I don't think I remember.
Yeah, you were really young. Yeah. Anyway, I wanted to talk to you about maths. How are you doing in school and all? How do you like the subject? Do you like it?
I don't hate it, but I don't love it either. I mean, it's there. I don't study it often or anything like that. I don't practice it.
Okay.
So I
Okay,
don't
so
do too well, but I don't do like horribly either.
Okay, so the way the Indian education curriculum is designed, it's not designed to make you fall in love with a subject. So
Yeah.
it's taught in a horrible way. It's done in a very routine sort of a way, and people lose interest. But the point of our class here and maybe future classes is so that you like the subject, and if you are interested in it, you can study it further. But the point is that the subject is awesome, and you should get to like it.
Hmm.
Okay. So you can think of this class as we will divide this introductory class into like sort of three parts, which are like key things that you need to know about maths. So first of all is about logic and proof. I
Okay.
hope you can see the screen.
Yeah, I can. I can.
So the first thing is that so basically maths depends on logic. There is nothing that is said which cannot be proved. And if it cannot be proved, you don't need to believe it, right?
Okay.
And everything is built up on a foundation of logic, so everything follows from certain logical assumptions and then you build on top of it. So that is a key criteria of maths, in which and in that sense it is different from so many other sciences. Even obviously it is different from other humanities subjects because there are a lot of opinions, right? And
Hmm.
nothing can be said to be completely right, or you cannot be sure, right? However, in maths, you can always be sure as long as you can prove something, right?
Yeah.
And it is different from other sciences also. For example, if you think about physics and chemistry, lots of times you will realize that in physics or chemistry, you will have heard of, okay, some laws that people have figured out, right?
Yeah.
But actually, those laws are also not like the laws of maths. Do you understand? Do you know why there is a difference? For
Uh.
example, I'll tell you Newton's laws of motion. You would have heard of it, right?
Yeah.
But there is a difference between Newton's laws of motion and Pythagoras theorem.
Hmm.
Do you have any idea what I'm talking about right now?
Not really. Like I'm understanding what you're saying, but I don't know the answer.
Okay, that's fine. So, Newton's laws of motion and all of physics and chemistry comes from experiments and observing the world around you.
Hmm.
So, it comes from seeing nature and trying to describe how nature works, right?
Okay.
But it turns out that Newton's laws of motion are also not really accurate for certain types of situations, like for really tiny situations, like microscopic situations, right? So,
Huh.
as long as you don't see those things, you will feel that this is correct. Okay.
Hmm.
So, basically, for all intents and purposes in the real world, you will realize that it is satisfying all our experiments and it is predicting nature very well. So you consider that this is correct, right?
Yeah.
But in laws in physics and chemistry are such that if an experiment later turns up and you see that the results are not agreeing with your law, then you will have to say that, okay, my understanding of nature is incorrect and I will have to change it and come up with a better theory, right?
Yeah.
So basically, they are always liable to change. For example, Newton discovered his laws in 1600s, but in 1900s, some of what he said was proved to be wrong, and people went on to a new theory of nature, right? Which
Hmm.
was called quantum mechanics. So what I'm saying is that the laws of physics and chemistry can change over time when you discover new things, right?
Yeah.
But that is not the case for Pythagoras theorem.
Hmm.
Like once it is proved, it is forever true, right?
Yeah.
There is a fundamental like difference. Like once you do something in maths and once you prove something in maths, it's forever true. Nobody can change that. There is no new thing that will come here. Okay.
Hmm.
So that is a difference, and that is the first part of the class where we'll talk about logic and proof, which more or less is the foundation of maths. The second part, and one of the more interesting parts of maths, is about patterns and weird things that happen, which weird things that you might see. For example, we'll take a few examples of numbers and all, and we'll see some certain things which people try to discover. Like people try to discover patterns and try to explain those patterns, right?
Yeah.
And that will be quite interesting. And finally, the third part of maths is probably the most important part as far as real life is concerned, which are applications. So
Hmm.
in case you are not into maths and you're feeling like, okay, maybe maths is not for me and it's not so useful in real life, actually that's not true because it's super useful. And people who don't understand maths later regret not spending time in their early years on that. Because no matter what you do in life, you will need some maths.
Yeah.
And an ability with numbers is always good. And it always gives you an advantage over your peers. Okay. So what we will do is three things. We'll look at some things here. We'll look at some things in this bucket. And finally, we'll look at these things. Okay.
Okay.
So the first thing that I want to start off with in the first section basically is about logic and proof. And I want to start off with the very familiar Pythagoras theorem.
Hmm.
You must have heard of it, right?
Yeah. Yeah.
So there is a right angle triangle, and in that thing, this is side A, and this is the base, which is side B, and this is the hypotenuse, which is side C, right?
Hmm.
What does the theorem say?
A square plus B square equal to C square.
Correct. So have you seen a proof of this?
I don't think so. I must have, but if I have, I don't remember it.
Okay, so one thing that is very important in studying any science is you should never be satisfied with someone saying something. Like if someone says, okay, Pythagoras theorem is true, you should never like take him on a faith basis. Okay.
Huh.
Like you have to ask why. And if you cannot explain why, then basically that's not serving any purpose then. Okay.
Yeah.
So you need a proof for this theorem. And I don't know if you have studied similar triangles in school, have you?
No, you mean congruency? Yeah, I have.
But similar triangles you have not studied yet, right?
No, no.
Similar triangles is in 10th grade syllabus, so it will come sometime this year, probably. So
Oh,
there is one proof of Pythagoras by similar triangles, but there are many other proofs actually. And what we will see today is a beautiful proof that once you see it, you cannot forget. Okay.
okay.
So I can sense some skepticism on your part, but you will not forget this proof. Okay. So this is the thing. What we are going to do is make a big square. Okay.
Okay.
And this square has all the sides of this square have length a plus b. Okay.
Okay.
So obviously it's a square, so all the angles are 90-degree, right?
Yeah.
And now what I will do is on this side, I will mark off b length. B, this much is b, okay?
Okay.
And this much is a, right?
Uh-huh.
So this point is p, let's say, okay?
Okay.
And on the other side also, again, I will mark a b length. Do you understand what I'm doing?
Yes.
This much would be A, right?
Yeah.
And on this side also, again, I'll mark a B length.
Okay.
And this is R. And obviously, again, here also I'll mark a B length, and this is S.
Okay.
So what have I done? I've just marked 4 points on the sides of a square, and I've called them P, Q, R, S, right?
Yeah.
And they are dividing each side in the B is to A ratio, B and A parts, right?
Okay.
And what we'll do now is we'll join these points. So let's join these points like this: PQ,
Okay.
QR, RS, and TS, right?
Yeah.
So because I'm drawing it with hand, it might look like it's not a square, but it is a square, this thing inside, okay?
Okay.
But again, because I'm saying it, it doesn't make it a square, right? Just because
Yeah.
I'm saying it, I have to prove it also, right?
Hmm.
So how do I prove that this figure inside is a square? So I'm talking about the figure PQRS, right?
Yeah.
So in order to prove that, what we will do is we'll call this angle here, X, okay?
Hmm.
And if you look at, let's label the sides also, A, B, C, and D, okay? So if you look at triangle ARS, can you see triangle ARS?
Yes.
In that triangle, this angle, let's call this angle capital A, angle A, okay?
Okay.
And let's call this angle B.
Huh.
Why am I calling this angle A? Because if you see, this is a right angle triangle, no?
Yeah.
And it's a right angle triangle with one side A, small a, and one side small b, right?
Hmm.
And I'm calling angle A as the angle opposite to the small a.
Okay, fine.
That is just a way of calling. It's a notation, okay?
Okay.
I'm calling this angle as capital A and this angle as capital B because it is opposite to B, see?
Okay, yeah.
This is also a right angle triangle, no? PDS.
Hmm.
In this, it is opposite to angle B, right?
Okay.
Now, if you think about it, you know that the angle on a straight line, the total angle on a straight line is 180 degree, right?
Yeah.
So can you see that angle A plus angle X plus angle B must be equal to 180 degree?
Yeah.
That is obvious, no?
Yeah.
And if you look at all of these right angle triangles, there are 4 right angle triangles, right?
Yeah.
Can you see that every right angle triangle has a similar nature? One side is A, one side is B, right?
Yeah.
Everything is actually identical. These are all congruent triangles, right?
Yeah. Okay.
Do you understand why congruent triangles?
Because A and B is the same everywhere, right?
A and B is the same and the middle angle is also same, right?
Yeah. Okay.
So it is SAS, right?
Yeah.
All 4 triangles are congruent, right? So if the triangles are congruent, then the angles inside the triangles also will be same, no? All 4 triangles.
Yeah. Yeah.
So all the angles will be angle B here, angle A here, and 90, right?
Hmm.
Similarly, here it will be angle A here, angle B here, and 90, right?
Yeah.
Are you understanding what I'm saying?
Yeah.
So basically what I'm saying is all the 4 right angle triangles are congruent, right?
Uh-huh.
And in each right angle triangle, the angles are angle A, angle B, and there is a 90 degree angle, and which adds up to 180 degree, right?
Yes.
So doesn't this tell us that angle A plus angle B is 90?
Yeah.
And if angle A plus angle B is 90, doesn't this tell us that angle X is 90?
Yeah. Huh.
Do you understand how angle X is coming as 90?
Got it. Got it.
So if angle X is 90 and I have shown it here, obviously I can do the same thing and show that this is also 90, no?
Yeah. So all four sides of all four angles are 90.
So all 4 angles are 90, then it must be all 4 sides are also now equal, right?
Yeah.
So it must be a square then, right?
Got it. Yeah.
And let's call this side as C, correct?
Okay.
So we are calling this side as C, and this is a square that we have made inside our big square, right? So now we come to the main thing. If you look at the big square, what is the area of the big square, which is ABCD?
Are you asking me?
Yes.
Oh,
Area of the big square ABCD.
yeah, AB square, right?
A plus B whole square, right?
Yeah, yeah.
Because the side of the big square is how much? How long is it? A
A
plus
plus.
B, right? It is A plus B whole square, correct?
Okay, yeah.
And this big square was made up of what? It was made up of small square PQRS plus four triangles, right?
Yeah.
And all four triangles are congruent, right?
Yeah.
So what is the area of the small square? If you see the small square, the area will be C square.
Uh-huh. Okay, yeah.
Sure, no?
Yeah.
Plus 4 times the area of the small triangles. What are the area of the triangles?
Half A into B, half into A into B.
Correct. So are you seeing that I am writing the overall area as the sum of the area of the small square plus 4 triangles area, right?
Yeah.
So it is coming out to be C square plus twice of AB, right?
Yeah.
And in another way, I had written the same area, and that was A plus B whole square, right?
Okay.
The same area ABCD I can also write as A plus B whole square also, right?
Yeah. So
So
A
is
square plus B square is equal to C square.
now you can equate these two, no?
Yeah.
If you equate these two, you can see that the 2AB term will get cancelled, right?
Huh.
Because the left hand side will be A square plus B square plus 2AB, and this will be C square plus 2AB, right?
Yeah.
So
Got
now
it.
we have proved that C square is equal to A square plus B square. We did not use this before. We did not assume it. We have now shown it, right?
Yeah.
So C was the third side of the right angle triangle. So this is the proof of Pythagoras. And
Oh,
most of the proof is just in the figure.
got it.
If you just draw that figure correctly, a big square and these inside square, and prove that this is a square, after that is just areas, right?
Yeah. Got it.
So the point is, there are many other ways to prove it also. However, this is a nice way to do it, right?
Hmm.
Okay.
Hmm.
One more thing that I wanted to talk about here was, uh, have you heard of prime numbers?
Yeah.
What are prime numbers?
They have no factors except for one and the number.
Correct. So examples are 2, 3, 5, 7, and so on, right? And you know that the number of prime numbers is infinite, right?
Yeah.
It will keep going on forever, right? Infinite primes.
Hmm.
Now, 2000 years ago, 2500 years ago almost, there was one guy called Euclid,
Yeah.
and he proved that the number of prime numbers is infinite.
Okay.
And he proved it in a very clever way, and that is what I want you to know.
Okay.
So, do you know the proof of this number of prime numbers is infinite?
No.
Okay. So you should know the proof because it's a beautiful proof and it uses this concept called proof by contradiction. Have you heard of this ever?
No.
Okay. So in 10th grade, I think in the first chapter, if they have already started, I don't know, but the first chapter is about numbers and all, right? Real numbers.
Yeah.
In that, you will learn about irrational numbers.
Yeah.
And maybe in your school, they will talk about a proof that root 2 is irrational. They will show you the proof of this statement that square root of 2 is an irrational number,
Okay.
right? And in school, have they done this before? They have not done it yet.
No.
Okay. So when they do that, they will explain this proof by contradiction method. However, I will tell you right now, the same method will be used there also. and it's a very powerful tool that mathematicians have. Okay, so many problems are solved by this method. Basically, if somebody asks you to show something, you can use this tool, which is called a contradiction proof. So what do I mean by that? So if you want to prove something, what the method does is you assume the opposite of what you want to prove.
Okay, fine, got it, got it.
You assume the opposite of what you want to prove. Okay, and from there you want to show that it leads to something weird or totally not possible.
Huh, okay, okay, fine.
Show that it leads to something nonsensical. Do you understand what I'm saying?
Yeah,
Even lawyers use this kind of a thing. Like they say that, okay, let's assume that this is not true, and then what would have happened if this is not true, and it leads to something not logical, then that means our assumption is wrong. Right?
yeah,
Do you understand what I'm saying?
yeah, got it, got it.
If you assume something and then from there you can prove that something totally weird is happening, then maybe your assumption was wrong. Right?
Yeah, okay.
So that is the method called proof by contradiction. Okay. So what we will do now is we will apply that method to prove this statement, just like Euclid did. Okay.
Okay, fine.
So what we will say, what does he want to prove? He wants to prove that the number of prime numbers is infinite, right?
Yeah.
So let's assume something which is not opposite of that. So what would be a statement that is opposite of that?
Number of prime numbers is finite.
Correct. So the statement that will start off with our assumption that number of prime numbers is finite.
Hmm.
Correct? Finite prime numbers. So if it is finite, you can probably list them out, right?
Yeah.
Like suppose the number of prime numbers was finite and the number was 10, right?
Mm-hmm.
If there were only 10 prime numbers, it's a finite number. So you can list all of the prime numbers then, right?
Yeah.
Let's call it n1, n2 till n, let's say whatever number, n100, right?
Hmm.
Do you understand what I'm calling? What these are all prime numbers, okay?
Yeah.
And this is our finite list of prime numbers, correct?
Okay.
Now Euclid said, okay, fine. Let's say these are my prime numbers. I'm going to make a new number. I'm going to make a new number, and this number is capital X, and this number is given by n1 times n2 times, multiply all the numbers in your list, right?
Okay.
Plus 1. Okay.
Got it.
This number is a new number that I have constructed, and it is the product of all the prime numbers which are supposed to be finite, right? And add 1 to it, right? Correct?
Okay.
Now think about this new number x. Think about x. Can you, now our prime numbers are which one? n1, n2 till n100, right?
Yeah.
So do you think n1 divides x? Does n1 divide x completely?
Uh, yeah.
Think about it. Does it completely divide x without leaving any remainder? Let's take an example. Okay. Let's take an example. Let's say let's say number of prime numbers was only 4, right?
Hmm.
We are taking the list of prime numbers 2, 3, 5, 7. Okay. This is my finite set of prime numbers, right?
Okay.
And the number that I will construct would be 2, 3, 5, 7 plus 1, right?
Yeah.
So see this, calculate this, 10 into 3, 30 into 7, 210 plus 1, 211, right?
Huh.
You think 2 divides 211?
No.
Similarly, do you think 3 will divide 211?
No.
Because when you do division, you'll see that 1 will be left, no?
Yeah.
Similarly, 5 will also not divide 211, right?
Yeah.
7 will also not divide 211.
Yeah.
You understand that all the prime numbers in your list will not divide this number. Right?
Yeah. Okay, fine. Got it.
So if all the prime numbers that you knew are not dividing some number, then that number itself is prime, no then? Do you understand what I'm saying?
Yeah.
Think about it. What are composite numbers? Any composite number will be divisible by any prime, right? Some prime.
Yeah. Like,
But
okay.
if you think of any prime number, do you think any other lower prime can divide it?
No.
So isn't this x another one of those numbers which none of the prime numbers can divide?
Oh, yeah, yeah, it is.
It is another one of those numbers, no, which is not divisible by any prime number in my list, right?
Yeah.
If my list was finite, let's say n1, n2 to n100, and I make a new number n1, n2, n100, product plus 1, right?
You're
Then you
making
should,
another.
correct. We are right now making a number which is not divisible by any of these, right?
Huh. Yeah. Okay.
So then x should also be prime, no then?
Huh.
So
So then,
shouldn't we now update our list and add x to it?
yeah.
And now can you make a new number after this again?
Yeah. You can.
So shouldn't that also be a prime then?
Huh. Got it. So
So
then,
this process will never end, right?
yeah.
So basically we are going on increasing the length of our list, right?
Yes.
So basically what he's saying is that the length of the list is not going to be finite.
Huh. Got it. So, yeah, there'll always be, yeah. So infinite.
So it's a contradiction to our initial assumption, no?
Huh. That, yeah.
Initial assumption was it was finite. And now we are getting, every time we can add new prime numbers to it, right?
Yeah.
And therefore it's a contradiction because now our list is infinite, right?
Yeah.
So our initial assumption is wrong, and so the number of prime numbers is infinite.
Got it.
Okay. So the proof is actually like super logical, and it takes like 3-4 lines to write. And this proof is probably one of the best proofs that you will see in number theory. So it's very interesting, and I mean, completely it works basically, right? Now, so I just wanted to show you two proofs because these are the kinds of things that mathematicians do on a regular basis. They cannot accept things and take it for granted. They have to show certain things, right? So,
Yeah.
and there is a beauty to proofs in the sense that once you prove something on your own, you will have that feeling of accomplishment. Okay. So right now the maths that you're learning is very rote based and very procedural in the sense you just learn how to do things, right? They are teaching you, okay, do this, do that, find this, solve an equation. But that is not the real maths that you are supposed to appreciate. What you learn as you go higher is basically how to look at an unknown statement, the statement that you have seen for the first time, and try to come to a proof of that, or try to show that it is wrong or it is right, right?
Yeah.
So that logical way of thinking is super important. Okay. Now, what I wanted to show you is we'll move on to the second part, which is about patterns and weird things happening and what mathematicians do and things that they discover. Okay. So, have you seen a deck of cards?
Yeah.
You have a deck of cards at home.
Yeah.
You have it, then get it. If you have something somewhere lying around.
Yeah. Okay, let me check.
Yeah. Yeah.
Yeah, got them.
Okay. You also need a calculator. If you have a calculator nearby, that will also be useful.
I'll just use my laptops, maybe.
Okay, okay. Fine. So now in that deck of cards, I want you to remove all the aces and all the face cards. By face cards, I mean kings, queen, jacks.
Okay, and ace?
King, queen, jack, ace, all of these, and also the 10 cards with the number 10. Okay.
Okay. And jokers?
That is the jack, the J, right?
No, there's an extra. I'll just take those out of there.
So I need only these cards remaining. Okay. The number cards 2, 3, 4, 5, 6, 7, 8, 9.
Yeah.
So basically, there will be 32 such cards
Okay.
because there are total 52, I think, in the whole deck.
Yeah.
So if you remove all the 4 aces, 4 kings, queens, jacks, and tens, tell me when you are ready, when you have removed everything.
Okay. Yeah, done.
Okay. So now this is like a magic trick. So you don't have to tell me everything. Okay. You just have to follow the instructions. Okay.
Fine.
So what you have to do is pick any 10 random cards out of these. Okay.
Okay.
Any 10 random cards.
Done.
Whatever you feel like. 10. Okay.
Yeah.
You did it.
Yeah.
Okay. Now without telling me the numbers that appear on the cards, just multiply them using a calculator.
All 10 of them?
All 10 of the numbers you have to multiply using a calculator and don't tell me the answer. Okay. And just write down the answer for yourself somewhere. It will be a big number.
Yeah.
Use a calculator and just write it down yourself. This is a fun trick that you can show to others as well.
Got it.
Okay. You have gotten that number, right? You have written it down, right?
Yep.
Okay. Now, in that number, you have to circle any one digit. Any one digit, which is should be from 1 to 9. Any one digit in that number, right?
Circled.
Okay, great. Now, slowly you have to remove all the remaining digits one by one. You have to remove all the other digits. Okay. And when you remove the digits, you have to tell me those digits that you have removed. Don't remove the circle digit.
Okay.
So, okay.
Can I remove a zero as well?
You can remove whatever.
Yeah, so I'll remove a zero then.
Okay. Slowly you have to tell me whichever numbers you are removing. You have to tell me that. Okay.
Yeah, I removed a zero.
Okay. Next.
I'll remove another zero.
Okay.
I'll remove a six,
Okay.
a four,
Okay.
a six
Okay.
again, and then another six.
Okay.
Yeah.
That's it.
Yeah.
Okay. Now I'll tell you the remaining digit. Is it 5?
Yeah.
Nice trick, right?
Huh.
So the
Wow.
remaining digit is 5, right?
Yeah.
If you want, you can do it once more. Once more to show the power of the trick.
Okay.
Pick any 10 random cards. Do the whole process again. Okay.
Okay. Four, five.
Don't tell me anything.
Yeah.
Once you have circled your digit, okay,
I'll let
first
you
you
know.
have to multiply and all.
Done.
Okay, you have circled your digit, right?
Yeah.
And now you can remove whichever one and tell me that whatever you have removed.
Okay, I'll remove a 0.
Okay.
I'll remove a 2,
Okay.
an 8,
Hmm.
another 0,
Okay.
a 3,
Hmm.
and then a 6.
Okay. And
Yeah.
the digit remaining is 8, right?
Yeah. Oh,
Okay. Okay. So what I will do is I will tell you the secret of the trick, but I'll not explain how it is working. Okay.
okay, fine.
So that you can also pull the trick in front of others. So I'll tell you what to do.
Uh-huh.
But what you have to do, the homework is to figure out why. Okay.
Okay, fine.
You have to try to figure out why the trick is working. I will tell you how to play the trick. So you know the process, what has to be done, right?
Yeah.
Basically, ask anyone to pick any 10 random cards. Ask them to, it should be from these number cards, obviously, right?
Yeah.
Ask them to multiply the numbers, right? And ask
Okay.
them to circle some particular digit, whichever one they want, right?
Yeah.
And then ask them to remove the remaining digits while telling me the digits, right? So when somebody tells you those digits, right?
Okay.
Correct. When
Yeah.
somebody tells you those digits, what you have to do in your head is keep adding them. So
Oh,
for
okay.
example, right now, what did you do? You removed a 0, right? And
Yeah.
then you removed a 2, right?
Yeah.
And then you did a 10, and then you did a 3, I think. No, something else. Uh, 10, 3, and then 6, or something like this you did. Just
Hello?
now, hello? Just now, what
Hello?
was the sequence of, can you hear me right now?
Yeah, I can. Sorry, I think my laptop glitched or something.
Yeah. So what I'm saying is you have to keep adding the numbers that the person calls out, okay?
Okay, fine.
So I think what you called out for me was 0 and then 2 and then
Yeah.
8 maybe. And
Yeah.
then what did you call 3 and 6, I think.
Yeah.
And if you can see the sum is coming out to be, I did the calculation, is 19, right?
Hmm.
And the reason I'm saying 8 is because you have to you have to see which is the next multiple of 9.
Okay.
Next multiple of 9 after 19 is what? 27, right?
Yeah.
The difference is the answer.
Wow.
Okay, so in the previous case, when I said 5, the sum was coming up to 13 or something.
Oh.
In the previous time that you did this, no?
Hmm.
The sum was coming to 13, so the next multiple of 9 is what? 18, right?
Yeah.
So I said 5, right?
Yeah. Got it.
And now I am saying 8 because it is 27, 19 plus 8 is 27, okay? Now, what you have to think about is, I will tell you the answer later, but I want you to think about it also. So what you have to think about is how is this trick working? Okay? What is
Okay.
going on? And you can obviously play it with your mom and dad also
Yeah.
and totally confuse them. Okay. So that is one. The other thing I want to do is another pattern. There are two more things that I wanted to show you in the pattern section. So this is another game. So you have to start with, so you have to start with any 3-digit number, okay? Where the first digit and the last digit should differ by more than one. Okay.
Okay.
Don't tell me the number. Okay.
Okay.
3-digit number where first digit and last digit should differ by more than one.
Okay, got it.
Okay, great. So now what you have to do is, second step is reverse the number.
Okay, done.
Okay. First step was choose the number. Second step is reverse the number. Third step is subtract the smaller from the larger. Use a calculator if you have to.
The smaller of the first and the third digit.
So when you choose this 3-digit number, right?
Oh, got. The reverse number and the
Huh,
normal number. Okay.
correct. So the first number that you chose and the reverse number, whichever one is smaller and all, you subtract the smaller from the larger, right?
Yeah, done.
And you will get some difference, right?
Yeah.
Okay. Now what you have to do in the last step is, to this difference that you get, add the reverse of the difference
There was the difference to what?
to the difference. You would have gotten a difference in step 2, right?
Yeah.
Just add the reverse of the difference to this, right?
Got it.
And now I'll tell you the answer is 1089.
Yeah.
So that is also a cool one.
Wow.
And you can try any numbers as long as first digit and last digit is different by 2. Differs by
Oh.
more than 1, right? You can,
Got it.
I hope you have written down the steps, because otherwise you'll forget the trick,
I have.
right? So try it for any other numbers also, it will work out. Okay. This is the second one. Third one is actually more serious. The first two are just tricks. The third one is a little more serious, and it was by an Indian mathematician called D. Kaprekar, and he found out in 1955 this cool thing. Okay. So what he did was, he started off with any 4-digit number. Start with any 4-digit number where which has at least 2 different digits. Do you understand what that means? It has at least 2 different digits, right? Can you hear me? There is something wrong with your connection, I think. Can you hear me now?
Oh, sorry, I was muted. Yeah, I can hear you.
Yeah. Okay. So you have to start with any 4-digit number which has at least 2 different digits. Okay.
Okay, fine.
Then, and suppose you have a 3-digit number. No, what you have to do is put a 0 in front and make it a 4-digit number,
Okay.
because anyway the value of this is same as 137. Now second step is, arrange the digits of the number in both increasing and decreasing order.
Okay, done.
Increasing and decreasing order. So you'll basically rearrange the number, increasing order, decreasing order.
Okay.
Then you have to do, subtract the larger from the smaller. The small, obviously smaller from the large,
Okay, fine.
right? And you get a new number from here, right? Which is like the difference, right?
Yes.
Do you understand? You have gotten a new number now, right?
Yeah.
And now this is like your program, and what you have to do is repeat the same process with the difference.
Okay, so I'll get the reverse for that also.
Repeat the same process with the new number, which is the difference, right?
Got it.
Okay. So take this number that you got at the end of the 3 steps and do the same step again on it, right?
Okay.
Now, when you do this and keep repeating this again and again, what will happen is eventually you will reach this number 6174.
6174.
Right.
1 minute.
If you use a calculator and do this process, maybe it will take less than or equal to 8 steps.
Oh wow. Okay, then I'll yeah.
what was your initial number?
1927.
Okay, so let's start doing it a little bit. We'll just do it once to come to a conclusion here. 1927, the larger one is 9721, right? And the smallest number in the correct order is 1279, right? Correct?
Yeah.
Subtract them, what is the answer?
8442.
Okay. Now we'll work with 8442. So the larger ordering is 8442 and the smaller one is 2448, right?
Yeah.
Subtract them.
5994.
Great. Now let's do 59. No, this is not the correct one. 9954, right?
Yeah.
And 4599, right?
Yeah.
What is it?
1 minute, I haven't done this one.
Yeah.
9954. 5355.
Okay, fine. So now it will be 5553 and subtract 3555, right?
1998.
1998. And now it will be 9981, right?
Yeah.
And it will be 1899, right?
Yeah. 8082.
Okay, great. 8082 has come. Now it will be 8820, right?
Yeah.
The biggest number that can be found. The smallest number is an ascending order is 0288, right?
Yeah.
What
So
is it?
8532.
Great. 8532 is in correct order here, and then you have 2358, right?
Yeah.
What is it?
6174.
And now, if you think about it, what is special about 6174? If you do it on 6174, let's see what happens. Okay. 6174 is my number, so it will be 7641, right? And then it will be 1467, right?
Yeah.
Subtract this.
Oh, it gives you 6174 again.
So do you realize that now the process has ended?
Yeah.
Because now the repeated applications will lead to the same thing, no?
Huh. Got it.
So it's like a program. If you have done programming a little bit, right? You have 3 steps of a routine and then you keep repeating this again and again, a loop, right?
Yeah.
And at the end, you're getting this number 6174, after which the function doesn't do anything to it, right? It gives the same answer back, right? So basically the point is this type of number, this type of a process 6174 is known as a fixed point,
Okay.
known as a fixed point of the process.
Okay.
So basically what that means is if you do the process, at the end you will end up on this and after that it doesn't change, right?
Okay. Got it.
And this number 6174 is also given a special name. It is called Capricor's constant. So in 1955, when the mathematician discovered this, imagine he was doing it by hand and I don't know how he would have figured this out also. Like how you would come up with a process like this or how you came up with it is totally mysterious. But finally it is coming and it is definitely working out, right?
Yeah.
So this is the third pattern that I wanted to show you. Now I want to finally, okay, one more nice one that I can tell you is this. This is an unsolved problem. Okay?
Okay.
What I mean by unsolved problems, you might have heard of you might have heard sometime that there are theorems in maths which are not yet solved, right? Which have not yet been proved.
Okay. Like.
There are many. There is one Riemann's hypothesis. There is twin primes conjecture. What are twin primes conjecture? I'll give you an example. So if you see twin primes, what are twin primes? Twin primes are primes like this: 3 and 5, 5 and 7,
Yeah.
11 and 13. Then there are 17 and 19. Can you see that these are primes that are differing by 2?
Yeah.
There are many such pairs, okay? Many pairs of prime numbers which are like this. Okay. So the conjecture was in the 1700s, someone said that there are infinite number of twin primes.
Okay.
What does he mean? Euclid has already proved that there are infinite prime numbers, right?
Yes.
He was saying that there are infinite pairs like this that can be found, right?
Okay.
Now, why is this called a conjecture? Because nobody has been able to prove it.
Oh.
Okay. So far, mathematicians have worked for more than 200, 300 years, but nobody has come up with a correct proof of this. Okay.
Hmm.
People have found prime numbers which have like hundreds of digits.
Yeah.
Basically, people have used computers and figured out very large prime numbers which are twin primes. Okay.
Okay.
But it is still not proved in the sense that even if you keep finding many such examples, that is not a proof.
Hmm. Okay.
Do you understand what I'm saying?
Yeah, got it.
Finding many different examples does not constitute a proof. Okay.
Huh.
A proof is a statement where, like Euclid did a logical statement and he showed it without taking examples, right?
Hmm.
What when you construct a proof, it is true for all examples. You don't have to worry about it, right?
Yeah.
But so far nobody has been able to prove it. So this is an example of a statement like that. Similarly, what I will show you is another statement which is called the Collat's conjecture, which is a very simple statement, but nobody has been able to prove it yet. Okay, so the statement is super easy and it says start with any positive integer,
Okay.
start with any positive integer which is greater than 1.
Okay.
This is the first step. Second step is if it is even, divided by 2, right?
Okay.
And if it is odd, if the number is odd, multiply by 3 and add 1 to it,
Okay.
right?
Hmm.
And then at the end of this second step, you will get a new number, right?
Yeah.
And then you have to keep repeating the second step. Do you understand what I'm saying?
Keep repeating as in?
Keep repeating the same step, second step on that new number.
Oh, okay.
So for example, let's do an example. So the example is, let's take any number, pick any number, whatever you want.
3.
So 3. So 3 is no 3 is a number, first step is already done. 3 is an odd number, right? Correct?
Yes.
So what should we do? We should multiply by 3 and add 1 to it, right?
Yeah.
So
10.
we'll get 10. And
Yeah.
now we'll repeat the same process. So 10 is even, right?
Yeah.
So what should we do? We'll divide by 2, right? Correct?
Hmm.
And do you understand so far what we are doing?
Yeah. Got it. Okay.
And if 5 is coming, then what should we do now?
Again, multiplied by 3 and add 1.
Uh, and now what should we do?
16 divided by 2 again, 8.
And then,
Again, you divide that by 2, 4. And then 2 again. And then 1.
so what this person said was that the sequence of numbers will end in 1,
Hmm.
will always end in 1.
Okay.
Do you understand what the
Yeah.
statement is?
Yes.
If you do this operation on any number, starting with any number, he is saying that the sequence will always end in 1.
Okay.
We just saw it work out for 3, right?
Yeah.
You can always check out many different numbers. And again, this was proposed in 1700, something like that. So for the last 300 years, people have checked it. It always works. but nobody has been able to prove this.
Oh,
Do you understand?
yeah.
Like every time it seems to work, but nobody can figure out the reason or a proper proof that says, ki, okay, this is why it works. Okay.
Got it.
So it is also a quite interesting situation. Okay, I'm going to now move on. These patterns are fine. Now we'll move to one or two examples of applications. Okay.
Okay, fine.
So applications are super important because that's why most of normal people do maths. So the first thing that I want to tell you about is, have you heard of this term called rupee cost averaging?
No.
Have you heard of anything like investments and investing?
Yes, yes.
So your dad and mom must have spoken about investing and all, right?
Yeah.
So suppose you have some money and it is better to invest. Let's say you wanted to invest in the markets, right?
Hmm.
In the stock markets and all, right?
Yeah.
So now suppose you have some money that you want to invest and another friend of yours has some money that they want to invest, right?
Okay.
And both of you have decided that you will buy stocks of some good company. Okay, you can buy stocks of say HDFC Bank or something,
Okay.
right? And your friend has a strategy that every week he or she will buy 10 shares
Okay.
of HDFC Bank every week, right?
Okay.
On the other hand, your strategy is every week you will invest or you will buy stocks of the same company, but how much rupees? Let's say the stock was right now at 100, so he's rupees 100, let's say, right? So your friend was buying 10 shares at rupees 100, and you are saying I will invest 1,000 rupees every week.
Okay.
Do you understand that both of you are spending the same amount in the first week?
Yeah.
Because the price of the stock is right now rupees 100, right?
Hmm.
So he is buying 10 shares, you are buying 1,000 rupees worth of stocks, right?
Okay.
But obviously the price of the stocks will keep changing as time passes, right?
Yeah.
So what you have to figure out is which strategy is better.
Okay.
Like on the face of it, both of you are investing the same amount of money in the same company, right?
Hmm.
Right now, he's also putting 1,000 rupees and you are also putting 1,000 rupees per week, right?
Yeah.
But you will realize that one of these strategies is much better than the other. Like you follow this method, your friend's method, or you follow your method. Okay.
Yeah.
And one of this is going to give you more profits as time passes. Okay.
Okay.
It is not very difficult to figure out. You can easily figure it out. Okay. So obviously a little knowledge of maths will be useful in designing a strategy like this, right?
Huh.
Uh, this is a very simplistic idea. So if you think about it for 10-15 minutes, you will understand it. Okay. And if you
Okay.
don't understand it, you will just talk to your parents. They will tell you why it is better. Okay. So I don't want to explain this or spend time on it, but you can think about it yourself. Okay.
Fine.
One of these methods is definitely better. You have to figure out which one is better.
Okay.
Have you written down whatever you had to write down?
Yeah.
You got it. No, you have any doubts, you need to ask me.
No, no. I've got it. Yeah.
Okay. And the last application or the second application that I wanted to tell you comes with a story. So basically, it is Second World War. Okay.
Mm-hmm.
Second World War, and the US is fighting Germany, is US v Germany. And the US Army is obviously sending many planes,
Okay.
sending many fighter planes to go and hit the targets in Germany and so on, right?
Yeah.
And this is actually true. All of this is true. So in the 1940s, this is happening in the 1940s. And they have also had some statisticians and mathematicians to help them do some analysis for them. Okay.
Okay.
So there was a group called the Statistical Research Group that was formed by the US government. And there was this guy in that group called Abraham Wald.
Okay.
He was a smart guy, and he was asked to give some advice to the US Army to figure out what to do or what should be better and all. And the exact advice that they had to give was how should they modify their planes or add armor to their planes. Do you understand what armor means?
Yeah, yeah.
So that it doesn't get shot down easily, right? How
Yeah.
should they add armor to the planes to better increase their chances of survival and all, right?
Okay.
Obviously, the armor cannot be added all over the plane because otherwise it will become too heavy to fly.
Yeah.
So you have to make some choices there, right? Now, what was the data that the army gave to the guy here? The data that they gave was this much. This table, they gave them the table like this, and they said that all the returning planes, whatever planes returned from their battles, right? This data was taken from the returning planes, okay?
Okay.
And the table had this information. This is section of the plane, and this is bullet holes per square feet.
Okay.
Do you understand what that means?
Yeah, yeah.
How many bullet holes it had? It was fighting, obviously, so it will have some bullets might have hit it, right? And
Hmm.
these are the different sections of the plane: engine, fuel tank. Then there is uh, rest of the plane, and then there is wings or whatever, right? These are the sections of the plane, and for each of them, the number of bullet holes per square feet in the returning planes was given. Okay, so
Okay.
the numbers are like this: 1.11, 1.73, 1.55, and this was 1.8, right?
Hmm.
Okay, so are you understanding what is going on?
Yeah.
So whatever returning planes came back, somebody must have counted how many bullet holes are there everywhere, right?
Hmm.
And based on that, they calculated this data they got. This many bullet holes per square feet for the engine, fuel tank, rest of the plane, and wings, right?
Okay.
And now the job of Abraham Wald is he is being asked to decide where should we add the armor to the planes.
Huh. Okay, fine.
His job is obvious. He has to advise the army, say ki, you should add further plates or iron plating or armor to this particular section of the plane. That will be better, right?
Yeah.
So take a couple of minutes, think about it. Where do you think we should add armor? Like we just have to decide which place should we add armor in using this data, right?
I mean, I thought the wings, but that's probably not it.
What you thought?
I thought the wings, but probably not it.
But that's what the US Army also thought.
Okay.
The US Army was also intending, okay, more bullet holes, right?
Yeah.
Wherever there are more bullet holes, let's add the armor there first, right?
Yeah.
But think about it for 1 or 2 more minutes. Think about it a little. Any reason why you can think of maybe the answer could be other than that?
Uh, I'm not sure actually. Maybe the engine because it's the most valuable. That's all I can think of. Not.
That's correct actually, but the reason is very interesting. And the reason what you're saying engine is most valuable, that is based on your prior knowledge, right? It's
Yeah.
not based on this data,
Yeah.
but you can actually explain it using this data also. Okay.
Okay.
So think about it. Actually, the order in which you should add the armor, you should first add armor to the engine, then you should add armor to the rest of the plane, then you should add armor to the fuel tank, and finally the wings. This is the correct answer, although it seems a little counterintuitive, right?
Hmm.
Why are we adding armor to the other parts where less bullet holes were there?
Okay. I don't know
Do,
why.
do you understand that it seems a little counterintuitive?
Yeah. Yeah.
Okay. The reason is very easy. These are data from the returning planes, right?
Uh-huh.
There are planes that did not return.
Oh, okay.
Planes that did not return means, like, think about what it means if this number was zero. Let's say this was zero. Think about it, what it means if the number was zero in some column, right?
Oh, so every plane whose engine was shot went down.
Yes.
Oh.
If the number is less here, then actually that means that if it was zero, suppose, right, then any plane that had any bullet hit an engine has not returned. No,
Yeah. Got it.
basically no plane has returned with a bullet hole near the engine, right?
Yeah.
So actually the number being less tells us which part is most vulnerable, right?
Got it.
Wherever the number is less, that means that part is the most sensitive, no?
Yeah.
Because the fuel tank or the wings are able to take 1.8 bullets and they have still returned.
Yeah. Oh, okay.
Do you understand?
Yeah. Yeah. Got it.
So basically, this is like an example of a totally real world situation, which is a historical event, right? So, where if somebody did not understand maths or statistics and the significance of numbers, they would do what the US Army would have done.
Yeah.
If they add up lots of armor on the wings and all, then it will lead to more planes being shot down.
Yeah. Got it.
So basically, I just wanted to show you certain interesting things to tell
Uh-huh.
you that even in war, even in totally unrelated sectors, even in corporate organizations, it is very important to have an understanding of numbers.
Got it.
And that number sense is going to help you whatever you do in life. Okay. So hopefully, like you you will find the whole thing a little interesting and you will get interested in the subject, but
Yeah.
definitely make sure to try the tricks on your parents,
Yeah. I will.
right? And try to figure out the reasons which I have not given. 2 3 things I have not told you so far, right?
Yeah. Yeah.
In a couple of games I have not told you the way it works, I have not given you the explanation, and in the rupee cost averaging thing also I have not explained which strategy is better.
Yeah.
So try to think of that and see if you can figure it out.
Got it.
Right now, I am not actually available for the next 10 days. So if we begin classes, it will be post June 10th.
Okay.
Okay.
Yeah.
So, and also, like, just letting you know, like, our classes will not be mostly about like 10th grade maths. Okay.
Okay.
Because 10th grade maths, I'm sure your school will handle pretty well. So, what we'll be doing is interesting maths.
Got it.
And we will do stuff that is similar to what we did today, but obviously today is like a trailer of the movie. The movie might not be as interesting. Okay.
Yeah. Got
So
it.
so sometimes we'll have to do some serious things also, right?
Yeah.
But it will be more interesting than school, that much is assured.
Okay.
Okay, okay, that's all that I wanted to tell you. If you have any questions, let me know. Otherwise,
I will. I will.
sure.
Okay, thank you so much.
Yeah. Bye.
Yeah, see you.